All right, everyone, welcome to the invited lecture. So slight change of program, Lindsay couldn't come, and Jean-Marie very kindly accepted to shorten his holidays and fly over. So he's going to talk to you about separation logic for the next few days. Take it away.
Thank you very much for your invitation. So please interrupt me. I have not rehearsed that much. That said, it's using materials I've already presented. So one is an intro talk about proofs of programs that I've done for math students. It's in French, so there might be, I mean, it was in French, so there might still be bits in French inside. It's reusing also material from the main course of separation logic I teach at Paris. Itself reusing some materials from Arthur Chargueiro a while back, and it's 12 hours long, but we should so I'll not present all of it, of course. So if there's something that goes too slowly or too quickly, please interrupt. Thank you. So I'd like to start with this picture. So it's hard to read. What is interesting is that it's a paper by Alan Turing. It's checking a large routine. So in fact, it's not that large, but it's used to compute the factorial of n without the use of a multiplier. So this is hard to read because it's a very old paper. But Morris and Jones wrote a small paper that rediscovered it. So this is called an organigram, I think. Like a flow chart with instructions. The squares are instructions, and diamonds are tests. And so the arrows are like a go-to or just the flow between instructions. And so the idea is that the boxes are the program, and you have annotations about it that says how do we prove this program. So I think it's considered one of the first proofs of programs. So it's an example saying giving a methodology to give proofs of programs. So the argument of Turing is that you don't have to understand all of the program to check that it is correct with respect to a specification. You only need to check little boxes. So you have the whole program here. The ingoing arrow is the precondition of the program, and the outgoing arrow here to stop is the postcondition. So here you assume that n is strictly bigger than 0, and you say that v will contain n factorial of n. And so yeah, for each box you check consistency between precondition, ingoing annotation, action of the instruction, so affectations mostly, and the postcondition of the annotation. All right, so nowadays, how is this done? So you have a more structured code. You have loops and functions. You don't have just arrows and go-tos. So you need fewer annotations. You need annotation on pre and post conditions and invariance on loops. So problem solved. So yes, in theory, but of course, those proofs are very, very boring. You have many
Uh,
They are also fragile. So when you do a proof, or when you write a program, you'll make changes very often. So every time you change, you're supposed to do the proof again, and so that's very error prone. You have also subtleties depending on the language. So you have if you have 2 to the 63, is it a positive number? Is it a negative number? That could be. Is it 0? That depends on the language. If you're using this operation, x plus x receives 1, is it forbidden? Does it have a non-deterministic result? Does the order evaluation of two function calls as operands of a plus matter? Should we worry about cache consistency of parallel programs? So all of those are not super interesting problems, but we're supposed to check them anyway. So that's something we we don't want to do manually. Of course, errors can be costly and dangerous. So the idea, I think I don't need to convince you of much of this, is that it's better to formalize each of those aspects using a computer proof assistant, and then to let's check everything. So I'll go quickly. So there was an intro talk. So this is the while language, toy language, or IMP. I'm guessing you know everything already about this. So just ifs and while loops. So this is the next one. So skip does nothing. This receives 1. This receives 2 times x, so it computes 2. This computes the absolute value of x. This computes, do you know? So yeah, maybe someone.
That's a very slow way to say n equals 0.
Yeah, so it is almost n equals 0, but not always. So it's 0 if we're working on with a natural number, or if it's in a cyclic element. Otherwise, if it's negative, you cannot terminate. This program computes something. You know? Yep. Actually, yeah. And this program is more complicated, but if you can guess. So the result is in X.
Wow.
Yes. Perfect. All right. So this is our program language, programming language, and so we have a Hoare logic. I'll go quickly. I'm assuming you know Hoare logic. Who knows Hoare logic? Okay, everyone, that's fine. So we have a bunch of rules. Maybe one thing I'll do is that usually when you prove something, maybe you'll start at the end, because that's a bit maybe easier if you have a bunch of assignments. So then there is weakest preconditions. Who knows weakest preconditions? 2/3. So the idea is that you almost start from the end, like as a principle. So you have WPSQ. That is the weakest precondition of S with the postcondition Q, which you can compute inductively on your language. So on skip, you do nothing. When you have an assignment, you do the assignment in the logic. You have a sequence. You don't need to introduce like for the sec rule in Hoare logic, you have this queue that you have to invent. There you don't have to invent it. You just compose the two WPs. For the if, it looks like the rule for if in the Hoare logic. And for while loops, you say a while loop is the precondition of a while B do S loop is there exists an invariant that is true at the beginning, and that is preserved by S. So assuming B and I, we can prove WP of S and I. And then postcondition is assuming not B. So some examples like this, I'll just follow. So the idea is that when you have a big program, you think really hard to find an invariant. This one looks fine. You run your WP, and then the program is in like a purple, if you can see it. And so when you unfold the definitions, you get a bigger and bigger formula. And at the end, you get something like this. So it's just unfolding the definition. And then you get something that is in fact false because you didn't think hard enough. And so in fact, what you're missing is, yeah, I'll pause a bit like this several times. So our invariant is missing something because you're supposed to prove that R is equal to x to the n, assuming that that I is less than 0, and R times x to the I is equal to x to the n. Yeah. Yeah, perfect. So you're strengthening your invariant with I greater or equal 0. And so then you can patch your whole thing up, and you have your precondition at the end that is n is bigger than 0. So that's very frequent, as you know. The invariant is not general enough, and you forgot the precondition. But then when you check, that's fine. All right, so that's the end. But so what does that mean? So you need to show that those rules were correct. So usually you formalize and you trust a small step operational semantics and configurations MS, where M is memory and S is statement. So those configurations step or don't step. When they don't step, they are stuck. And stuck means you are going wrong. There's something going wrong. Then you need to define P of M to say this memory satisfies P. And then your PSQ is in fact, it means the following. It means that if you have a memory that satisfies P and nothing goes wrong when running MS, and for all of the results, when you run MS and you reach skip, then you have Q of M prime. So that's so you're assuming that you terminate, and you prove that all of the memory on which you terminate satisfy the postcondition. All right. So that was one presentation, but it was one way. The other way around, I think, is more used. So usually the rules of the separation logic are not rules, but just lemmas that are talking about the semantics. And WPS is not defined by WPSP. WPSQ is not defined by induction on S, but is defined recursively or inductively, depends on the steps. So you say that WP of skip and a postcondition Q holds on M if Q of M. And then for the recursive step, you can prove that WPSQM holds if F S and M is not stuck. So there exists an M prime S prime, so that the configuration steps. That means that this configuration is not stuck. It's there's no bug here. And for every step that it can take, you have still WP of S prime Q M prime. So if you make this an inductive definition, this gives you you know that your program will terminate on skip and in all of the branches. So if you have a non-deterministic language, that's the better approach. Works well. It also works inside. So it's currently the one we use in Iris, which is the separation logic that is on fashion now. You can also have, so you have many variants. So inductive means that it will terminate. You have co-inductive, or you have also just a circular definition with a modality that is introduced, and that's the Iris thing. So if you do that, then you don't have termination guaranteed. Depends what you want. All right, so that was the introduction. Was quick, I think. Please interrupt me. So let's skip this to slide 21. Okay, so that was whole logic. I didn't talk about separation at all for now. So you have so that the first part, you have indeed mathematical proofs for imperative programs with variables. But when you start to have some pointer aliasing, when you start to have more complicated programs such as concurrent programs, it kind of falls apart. It's very hard to use. You can reason about those aliasing, but it's hard. Separation logic is the next version. It's whole logic with a more robust notion of memory. You can allocate things on a heap. You can do operation pointers. You can, and also it's robust in the sense that you can extend it to a bunch of other programming features, such as concurrent programs or algebraic effects or other things. All right, so a short history. So we have to cite those papers, but it was mostly in 2000 by Reynolds, Owen, and Ping. And you have this is a slide that is a bit outdated. I added some new things at the end, but it's just to say that there are many instances of separation logics. The picture should be much larger than this. There are papers that have like a graph of dependency between all of those, but it's big. So separation logic was quite successful, and it still is now. I guess, yeah. So you have automated provers. So like Infer by Facebook, you have a bunch of other ones. So they find many bugs. They can examine large code bases, and that's great, but they don't find proofs, only errors. You have semi-automated. That works well in some classes of programs. You have to provide invariants. But the problem is, the main problem I found when I'm using those is that when you have when you write an invariant and you don't know why it doesn't work, it's hard to debug. It's a black box. You don't know why it doesn't work. You don't know. Some people like it. I prefer interactive proofs. So I've worked on VST. I've worked with Iris. So typically they can combine a nice set of features. They can be formally verified. They are typically easier to debug. That's arguable, but I found that that's true. They are also expressive about, so both the programs they can reason about or can have features that are complicated, but also the proofs themselves can have complicated reasonings, but of course it's slower. So I will use, so in most cases, when you do separation logic, it's inside a logic framework. Here I will use Cut, the proof assistant, Rock now, and Iris, which is a whole proof mode inside of Cut. So what does it look like? So this is a Emacs buffer, ongoing proof. Left is a proof script that is validated. On the right side, you have at the top, you have the Coq hypothesis. So n is a natural number. H step is the hypothesis that sigma m steps to sigma prime m prime. And then you have other hypotheses. So the line here is the limit between the Coq hypothesis and the Coq goal. But the Coq goal is in fact itself a bunch of hypotheses. So this is an Iris hypothesis. This is an Iris hypothesis as well, and this is the Iris goal. So you have a whole mode inside of Iris to prove to do suppression logic. And if you want to hack at it, you have a bunch of tutorials available at irisproject.org if you are more of the hacky type than the listening type. So you can go there. Even click, but it won't do anything for you. I mean, maybe I can. No, never mind. Okay, so this is the end of the introduction. Now I'll teach about suppression logic. So first, maybe I should clear things up. So what is the heap in programming? So it's not heap like a heap sort. It's a heap like a thing that you have dynamically allocated. So malloc in C or new in other object-oriented languages. A bunch of sizes implicit. So like in Python, JavaScript, or Camel, you don't have those malloc or new, but you still have allocation in many places. And most things are on the heap. So except local variables or sometimes other things. So there is a stack, but most things are on the heap. Yeah.
So there are some language implementations where what would be the stack is instead a pile of activation records on the heap, which as an implementation detail doesn't matter very much, but correspondingly, there are lots of situations where it's a common technique to reify what would be the stack into an actual heap object.
Mm-hmm.
And I figured it was worth mentioning that now and getting it out of the way, because whether something is a local variable that we don't talk about as heap or not is slightly more subtle than.
Yeah, it is. It is so. In particular, in VST, the thing I've worked in. So VST is a proof framework for C based on ComStat. One particular thing about C is that you can have references to local variables, and so that adds a lot of complexity. The main thing I'm working on now is problem logic for OCaml, in which all of those things are, I mean, even some things on the heap are considered pure, and so you have almost like the other way. You're using a bunch of things that are on the heap as if there were pure things on which you are not supposed to reason about, like not with separation logic. So yeah, you have of course it's more complicated than that. Yeah, thanks. Okay, so what are heaps? Heaps are partial functions from locations to values. So I talk a bit about this because it's easier to be precise, at least at the beginning. So it's just subsets of x times y. So that's the definition of partial function, but heaps are partial functions. Yes. So finite sets of pairs that are functional. You have the empty heap. You have so those two things are heap, but this is not a heap because it maps two different values to the same address. And when the domains are empty, you write this U plus for the union. All right, so you have a bunch of heap predicates. Heap predicates are predicates on heaps, which means that if H is a heap, then H of H, big H of small h, is a proposition. So in fact, that would mean that H is of type heap or a prop, or the prop is the type of propositions. So you have a bunch of things. You have the empty heap, you have the pure fact P, you have singleton heap L maps to V. So you have the most important one, which is a separating conjunction, H star H prime, and you have a existential quantification. I'll just go briefly about all of those. You have so the empty heap and pure facts are predicates that take a memory and say the memory is empty, and for the second case, the memory is empty and P is true. So if you have let A is equal to 3 and B is equal to A plus 1, then the precondition of this would be empty heap, and the postcondition of this would be also empty heap, but knowing that A is equal to 3 and B is equal to 4. And empty heap is equivalent to empty heap with true inside. The singleton heap is saying that you have a memory. It's a singleton heap, and it contains the pair LV, location value, and L is different from null. So when you have a let R is equal to ref of 3, an allocation in OCaml syntax, then the precondition is empty, the postcondition is R maps to 3. All right, so the specification of increments of S is S maps to N before for some N, and after S points to N plus 1. So this is all supposed to be simple to understand, but so at the moment where you don't understand something, please tell me. That's designed to be simple, but okay. So separating conjunction is the important part, the most important one probably. So H1 star H2 characterizes maps heaps that are made of two disjoint parts, one that satisfies H1 and one that satisfies H2. So for example, if you have R maps to 3 and star maps S maps to 4, you have two different distinct reference cells. Even yeah. So the definition itself is that H1 star H2 is satisfy all of the heaps such that there exist M1 and M2 heaps that are disjoint, that are in the sum of which is equal to M1 satisfy H1 and M2 satisfy H2. Okay. So usually I give a bunch of exercise to my students asking, give a bunch of heaps satisfies all of this. I don't know. So, yeah.
I have a question about notation,
Yeah.
or like what the things mean.
Sure.
So a heap predicate is a function that takes a heap and returns a proposition.
Yep.
In the notation that you're using, it looks like you're manipulating programs rather than heaps themselves.
Those are formulas.
If you go back, for example, twice, you have the let example.
Yeah. So for now, I'm
Or
talking about the predicates. So this would be a program, and the rest are, and this is a program as well. The rest are propositions. Predicates. Sorry. All right. Okay, so you have a bunch of so this proposition is predicate is empty, so it has the empty heap satisfying it. This is false, so it has no heaps satisfying it. This has the empty heap as well. This is false because you cannot split any heap into something that satisfies nothing. Singleton heap, two heaps together, and those are leaking. So 1 points to 2 and 2 points to 1, so it's like a secular, two secular pointers. Yes. I can also repeat the question.
So for the last example, when you say it's a cycle,
Yeah.
so there's not a conceptual difference between locations and values. in
Yeah,
those operations?
if you want to be precise, there will be differences. But for now, we're saying that everything is just net.
Thanks.
Except and no 0.
For the one before that, it's never satisfied, right? Because you have the same address.
Oh yeah.
to-
You're right, absolutely. This was the important bit. You have two predicates that map something to one, and so you cannot separate anything into two disjoint thing that are domain 1. So if you have a simple program that allocates 2 references, let R is equal to ref5 and S is equal to ref3 and T is equal to R. So the first ref is an allocation, the second ref is an allocation, and the third thing is not a ref, so it's not an allocation. So if you run this, and so if you want to specify this, you should not give this as a postcondition, because T would not be able to be separated from R. So you have, this is the case of aliasing. So this is the first thing that separation logic was used for. And so if you would do incr, so of R and then incr of T, it's in fact the same reference cell. So you're supposed to specify it like this: R points to 5, S points to 3, and T is equal to R. And then the only thing that's incremented, it is the 5 to 6 to 7. Yeah, I can repeat.
Maybe I missed one of the things, but can you explain again why you couldn't separate if the values are different? I understood why if S and R are the same, I understood that, but why if the values that they're pointing to are different, why can't I separate them?
If the values are different, why can
So
you?
you're saying you said you cannot separate that because both R and T are pointing to 5.
Yeah.
But that's just the value they're pointing to, right?
No, so R and S and T are pointers, locations in memory. The actual value they have is a location, is an address. So how you specify them is that R points to 5. So you're not saying that R is equal to 5, you're saying that R points to 5, which is the heap there is a pair of R, 5. This is the heap thing. So you have in memory at the address R, you have the value 5. And so when you say T is equal to R, is that the two addresses are the same. Was that clear things up? Not really.
Not really.
So
It's just a theological. I think that helps.
It's just,
It'll help you.
well, if I'm the only one that doesn't get it, it's fine.
so you have it would be something like you have a this is the R, this is the 3, the 5, and the R is any address, say like 32, and R is also equal to 32.
which of the conditions, you have a bunch of conditions there when you're defining the separating conjunction, the slide before.
Yeah.
Which of the conditions is not met?
So you have the R points to 3 satisfy this, S points to 4 satisfy this, and the fact that T is equal to R is a pure fact. So it would be in either of those cases. You could like be also next to it. So it would be this. It would be, the information would be a pure fact. It would be stored in not in a heap, but just in the truth value of T is equal to R. So that's why we write this thing. So this is the one heap, this is one heap, and this is one empty heap. So all of those 3 heaps are separated. So if you want to prove to have this, to specify this with this postcondition, you will have a problem because you cannot establish that this is separated from the rest.
Okay, so what you're saying is that would not be a wrong, like that's a, there are heaps that satisfy that,
Exactly, yeah,
but it's not the one that you're trying to model.
indeed.
Okay, I got it. Thanks.
Yep. Thank you. Yeah.
Would it be another correct answer to start with, let's call the variable I'll introduce A for aliased, A to 5, then S to 3, T, and then the facts T equals R and R equals, sorry, T equals R equals A, T equals A.
You said 18 or A?
A for
Like,
aliased.
For a variable.
As in the aliased address.
Wait, like in the variable for an address or something else?
Yeah.
Like if that's
This is one of those things where it would be easier if I could write it out quickly, but if I started with and for the first one, A is assigned to 5, where I've made A out of whole cloth to talk about.
Are you wait? Are you talking about the program or the specification?
But the specification.
Yeah, like
So-
with the let here.
If I replaced that R with a fresh variable A, and then added 2 new facts at the end that say R equals A and
Yeah,
the deducible T equals A, would that be sufficiently equivalent? And
sure. Yeah, that is equivalent to there exists A such that blah 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 and R is equal to A. Yes. There would be rules for existentials
Yeah.
after. Yeah.
okay, I see why you didn't do it that way here now.
Yeah.
Can you go back a few slides to the definition of the heap and the definition of the points? Yeah, so heap first and then.
Heap.
Yeah, so partial function from X to Y on locations. And then if you go to the definition of L points to V, the predicate. So L is going to be in the domain.
Yep.
And then if you go to the slide that you were on with the example. So what's the relation between the program variable R and the R that you've written in the specification? Because you've also said R is just a number. in the
Yeah,
other
yeah,
example.
yeah.
So what's the relation between all these different variables? Is that like a meta theoretical quantification that you have, like you're saying, for all possible values R that the program could actually generate when it did the fresh reference cell?
Yeah.
Or what? Yeah.
So it is So the question is, how do I relate this R to this R? And this is a very, very, very valid question. The short answer for now, but it will be precise, that ref5 will return a value that you can put talk about in the post condition. So in fact, your program variable will not be the same as the logical variable that corresponds to it.
Okay, so these R's and S's down there are like meta variables. It's not like in the formal syntax. It's actually just a value.
Yeah, no, yeah, you can see it. It's in italic there, and it's.
Okay, thanks.
Thank you. Okay, so just to know what you can do with this, so you can so say you have records in your programming language, like a record head and tail for a mutable lists, linked lists. So you can add things on top of your. Say you have all of your basic predicates. You can say that p dot f points to v is actually some shortcut. So you want to say that p dot hd points to some value x, and p points tl points to some value p prime. And so you can encode this simply as saying that, in fact, hd and tl are some offsets. hd would be 0 or tl would be 1. And in fact, when you write p dot f points to v, it's just p plus f points to v. So then records field are just encoded. So when you say that when you want to represent list cells, so you'd like to have something to talk about in your language, so you encode a bunch of things. So you would say, so this is a definition, p points to some record hd is equal to x, tl is equal to p prime, is in fact defined as p dot hd points to x and p dot tl points to p prime. And so you can write it as this to be a bit shorter. This squiggly arrow will be used a bunch. In fact, usually it depends on your type, on your data type. You have that can be made formal, but it basically overload this notation with a bunch of different data types. So for pairs, for records, will be defined as a case analysis. So finally, and not least, there is existential quantification. So there is a symbol like there exists x.h. There is a double bar, but I might forget it sometimes. So there exists x.h is defined as all of the heaps such that there exists an x such that x of m. So of course, the important thing here is that x can depend on m, which makes it way more expressive. And so the types of those two things are those are props and those are heap predicates. Okay. So you have a bunch of I mean, you should just look at those and try to imagine which are the heaps that satisfies those heap predicates. I'll go slow. I mean, I'll read them. So there exists an x such that x1 points to x, but it's inside of those brackets. So that's an error. It's a typing error. You shouldn't write this. This is bad. You have a heap predicate inside of something that is a pure heap. Not good. You have there exists x such that x1 point to x and 2 points to x. So that's fine. That's just a heap with domain 1, 2, with the same two values. There is this x so that x point is equal to x plus 1. That depends on what this means, but probably that has no heaps satisfying this. You have to squint a bit more for this one. So x points to x plus 1, x plus 1 points to x. So that's the cycle we have before. This is the valid version of this, and this is fine. What about this one? Not good. Yeah, so it's not good because it's supposed to be two disjoint things. Plus, it's two different values. But even if the two values were the same, that would have been fine. So what are some heaps that satisfy this predicate? Yeah, that's fine. Yep.
Can you elaborate that if the two values were the same, that would have been fine
Yep.
because you say take the disjoint unit.
No, sorry. I said fine. It would have been not fine either way. It would have been satisfied by no heaps, even if 1 and 1 were here.
Oh, okay.
Sorry, it was my bad. So P would be a proposition here based on the implicit type would be proposition. So there exists a proposition so that pure fact of P. Yeah.
Okay, so I have maybe finish your example and I have a basic question.
Okay. So how many, okay, so one heap only satisfies this, which is the empty heap. And this is a bit more interesting. There exists an H such that H, and so this the H is there, and so it's a heap predicate, and so how many heaps satisfy this one? All of them, perfect. All right, question.
Sorry, it's just a naive question about heaps. Why is it clear? I mean, maybe there is no answer, but why is it clear that the star operator is kind of so fundamental for heaps? I mean, why is it what was the point of using that as a?
It will come. It's supposed to simplify local reasoning. Like you prove something about a program, and you prove something about another program. You can compose them sequentially, or even in parallel, which we'll see, and they still work. Yep. Here.
I think I might have misunderstood something with the second to last example. Could you just explain what's going on there? It looks, the way I read that, it looks like it would be there exists a proposition which is true, which specifically on the empty heap for the exists P.
So the exist P. So
yeah.
this is set. So if you remove the existential P, that's satisfied by all of the heap that are empty, and when P is true. When P is true.
Sure.
So the P doesn't depend on the heap. It's just this says that the memory is the heap is empty and P is true. And so if that's equivalent to the heap is empty and there exists a P such that P. Yes.
Where exactly is the requirement that the heap is empty coming from?
Like the brackets, the corners. So that's the definition is there. Like the heap
Okay,
is empty.
right. Okay, I misunderstood that. Okay, thank you.
Okay.
So I think my question comes from the fact that I still haven't understood what a pure fact is yet, but could you, so the first one, well, why is the first one bad?
Yeah, that's the first.
What is a pure fact? I still haven't caught that.
Because you're supposed to have some proposition here, and so this is defined as a predicate. So it needs a heap to become a proposition. So if you had a heap, or if you wrote the empty heap afterwards, then this becomes a proposition, and you can say that it's a true fact. But typically, you are not able to talk about the current heap in pure facts.
So pure facts are propositions.
Yes.
Okay.
Yes.
And also, I still haven't got the far left one at the bottom. I didn't get why.
So this one cannot hold on any heap, because when you're using the definition of the separating conjunction. So separating conjunction means it separates the heaps, like the domains, and it's here. The domains are supposed to be disjoint, like this. And so if you have a heap that satisfies x points to 1 and another one that x points to 2,
okay.
the domains needs to be x, like the singleton x,
Then
and cannot be disjoint.
Okay, thank you.
Thank you. Okay. So thanks for all of those questions, because I try to be clear, but yeah. So that's a summary. If you have a question still, it's there. So I'll just move on. So the first thing.
Then I just have a question
Sure.
about the formal status of offsets. Like, you had positive offsets, can you have negative offsets? Can you?
Yeah, we don't. It doesn't matter. You can. I mean, we don't use negative offsets, but I don't see a bad reason that would be. It would be a shame, because sometimes you're supposed to prove that something is different from null, so then you get some extra conditions on your main pointer. So the typical example is linked list in separation logic. So that was like the first paper, that was the first example. So I'll talk about linked list like a C style. So you express them in a camel, not like a normal camel list, but records with mutable fields. So you write it like this. You have a cell that is of any type. The field head is of this A type, quote A type, and the tail is of the same type, like it's a recursive type. So in practice, you could have this record, HD is equal to 8, TL is equal to some record, where HD is equal to 5, TL is equal to some record, where HD is equal to 6, TL is equal to now, and that's it. So it could be represented like this. You have at address P, the record 8 P1. At address P1, you have the record 5 P2. At address P2, you have the record 6 no. Of course, those what is interesting here is more the P than P1 and P2, because you could forget about P1, you have a pointer to it here. So we typically write this as follows, like P points to, the points to means the address P has this content. So the content at address P is 8, and some value of which that points to 5, and to the record 5 and some other address that points to 6, and that the record 6 and some address that is equal to now. Question here? Yeah.
So just to see that follows. So P has type ref alpha cell. Oops, sorry. P has type ref alpha cell.
Yeah.
That's the same type as tail as well. It's just OCaml as a mutable means ref alpha cell, right?
So there is no refs, but
it says mutable. So how do I read?
So mutable is so ref is implemented with a mutable record rather than the opposite. So it says that you can modify HD, you can modify TL, and the type of TL is the same as the type of.
OCaml also has ref types, right? So how do they compare to?
So ref is just the data type A content with content is mutable. A ref is the record, content is a type.
Oh, I see. Okay, so mutable records are the primitive.
Yeah.
Okay, thanks.
All right. So say when I write this, it means so that's OCaml notation to say A8 const 5 const 6 const nil. That's a pure list, and you could, when you write this is OCaml. This is pure. There has nothing on the heap. Of course, it is really on the heap, but we don't talk about it in separation logic. And when you have a mutable list, we write it like this, like a bunch of boxes. So if you want to say that P points to the list L, and the list L is this one, 856, then how do you formalize this in separation logic? You have to say something like this: P points to this record, and in fact, the second value here is not important, and we should not be able to talk about it. So we hide it behind a quantifier, an existential quantifier. So we say there is this P1 such that P points to 8 and P1, and separatedly, there is this P2 such that P1 points to 5 and P2, and separatedly, there is this P3 so that P2 points to 6 and P3, and separatedly, P3 is null and empty heap. So this work for this list. Of course, we can generalize to arbitrary list. Yes.
So just to confirm, the existential quantifiers really do just work left to right.
It is what did
the scope of an existential quantifier? There's not something going. Yeah, no. Let me rephrase this slightly. How would you put parentheses around all the separating conjunctions?
Yeah, that's fair. I like alignment, but this is not correct. It's supposed to be a big parenthesis here, opening, a big opening one, a big opening one, and they are close here. Okay. I mean, obviously P2 appears inside the scope of the existential P2, etc.
Right. So trying to say.
Okay. I don't know what that means for
quantifiers gobble as much scope. as
Yeah,
that.
I would-
So you've got a dot.
Yeah.
Up to the latest dot, so.
Yeah,
we have
it-
the
it-
dots in scope.
Yeah, like everything in the future will be inside the scope. So I would put, I typically try to put parentheses as little as possible, as few as possible. All right, so how do you define it in general for all lists? You define it by induction on lists, which is easy because lists are finite. So you do p points to L. If L is nil, p is equal to null. And if L is cons of x and L prime, there exists p prime such that p points to x and p prime points to L prime. I would guess no surprise, but still I have a nice picture. P points to this cell, and you have a big star between this cell. So this star here is between the cell and the rest of the inductive definition, recursive definition. Yeah. In general, if the question is short, I can just repeat it.
Okay. So the point is that we want to rule out things like a snail list and stuff like that, right? We
Yes,
just wanna-
exactly. So that forbids secular lists. If we can write them, but you have to be very explicit about those.
Thanks.
Yeah. So thank you, Han. So indeed, this implies no cycles.
Oh, sorry.
So if you have P1 that points to L1, P2 that points to L2, P3 that points to L3, you know that all of those are very separated. There is no sharing, no cycles. Yes. In some logic, you can write things like the following. So what's the problem with the following is that there is no clear recurrence going on. So that would be a circular definition. And that's fine sometimes. It depends if your logic is expressive enough. You can say, oh, this is the least fixed point such that. So this is equivalent. In general, when you write this, I mean, it's if you're writing something in a proof assistant, typically it's easier to write this, but you can know that in most modern logic, you can write something like this. That says there is a call to mlist even if you're defining mlist. And yes, we're introducing this operator, which is an OR. Okay, so maybe I should read it. So P points to L if L is nil and P is null, or there exists X, L prime, P prime, so that all of those are true. And so L prime here is just existentially quantified, so you cannot know that it decreases. In fact, you know that it could not decrease if you have like an infinite memory. I mean, it could not terminate if you have an infinite memory, but that could still be fine in some logics. But that was mostly to introduce this union heap predicates, which is an OR just pointwise. Okay. All right. So let's see a first program. So let's say you want to build a list of a constant list of size n. You have this function. So I guess you're familiar with a camel. Who's familiar with a camel? Okay. Who understands this? All right, that seems fine. So recursively, if n is equal to null, to 0, we return null, the address. Otherwise, we allocate, we call ourselves recursively with n minus 1 and v, and then we allocate this list cell, which hg is equal to v and tl is equal to p prime, the result of the recursive call. So if we want to prove this function, we'll have typically a precondition that says n is bigger than 0, and you have some postcondition that is the interesting part. The postcondition would be if p denotes the result, which is the kind of approximate way of talking about the result, but will be precise later. So if P denotes the result, then there exists some list such that P points to M list of L. The length of L is N, and every element inside is equal to V. Of course, you could write it a bit simpler by saying P points to M list of and then you have a meta logic that in your meta logic, you have some definition that says basically the same thing, and you have a P points to M list of repeats N V. So both are fine. It depends on a bit on your style of proving. Sometimes you want something to go like this. There exists some list, we don't know which one, and a bunch of properties about it. So there is a proof of this, but let's not do that. Okay. Let's do this more interesting piece of code. So this is a program that does list reversal. Maybe should I?
Oh, yeah, sorry.
Yeah, I mean it's a bit of a mouthful. So I mean you can read it. It's fun. Oh, perfect.
Homework.
Yeah, homework. All right. I guess I'm stopping now. Thank you.
Just quickly, could you go back to the slide where you were showing the mutable list?
Yeah.
So you had something like P2 goes to P3, P3 goes to null, or P2 goes to P3, P3 equals null.
Yeah.
Why could you not do P2 goes to null there?
Oh yeah.
Would that not type check, or would that be different semantics?
TL is equal to null is perfectly fine.
Oh,
It
okay.
was just to make it easier to discover the inductive
Okay.
definition.
Thank you.
Thank you. Yeah, it was.
Lunch?
Okay.
Yeah, sorry, I was too focused on the lecture. I didn't.